Hi everyone. Today we're going to be talking about integrals. Calculus is really divided up into two distinct sections. The first section, all about derivatives. The second section, all about integrals. So today we are finally transitioning into that part two of calculus here, integrals. So the question is, what is an integral? Well, it's related to the area under a curve that we saw in our last video. Specifically, it's an answer to the question, well, RAM is really not the best approximation. Can't we do better? You might recall that the formula to find the area under the curve that we'd been using was the sum from I equals 1 all the way up to n, if we have n rectangles, of delta x, the width of each rectangle, times f of x, I. This was what we'd been using. And the question is, well, can't we do better than this? Can't we do better than having n rectangles that are all this wide? And the answer is sure. And there are a couple of ways that we can do this. But the most common way that we do it is we say, all right, well, instead of having 5 or 6 or 7 rectangles, what if we had so many rectangles? What if we had more rectangles than we could count? Each rectangle would be getting thinner and thinner and thinner and thinner, so the portion that we miss under the curve would be getting smaller and smaller and smaller and smaller. So we might write this as a limit as n goes to infinity of this sum. Right? Because really what we're doing is we're saying, let's make infinitely many rectangles. What happens? And it's an interesting question because the more rectangles you make, the more delta x shrinks. So for instance, if you were on an interval from 0 to 50 and you wanted 50 rectangles, each one would have width 1. If you wanted 100 rectangles, each one would have width 1/2. If you wanted 500 rectangles, each one would have width 1/10. And you can see that in some kind of interesting balancing act, this gets much smaller, this gets much bigger, so the sum actually doesn't head to 0, which some people might think if the width is going to 0 of each rectangle, but it actually better and better and better approximates the area under the curve. As we go to infinity, this notation becomes a bit cumbersome, so we'll invent new notation. Let's say we're on an interval from a to b, and let's make those both inclusive. So this is our RAM approximation. But as we just discussed, if n is going to infinity, delta x is getting closer and closer and closer and closer to 0. So the way that we abbreviate this is with something called a differential. And we've actually seen differentials before, even though we haven't really called them that. This delta x is going to turn into a symbol, and that symbol will be dx. D for delta, again, represents change in. This whole symbol here, this sigma, which is the Greek letter S, which stands for sum, now becomes another thing that looks like an S, also for sum. So we would write it as the sum from a to b of f of x dx. This is our new notation that we'll learn today. This is an integral. The nice curvy S is the symbol for integral. The f of x here is called the integrand. It's what we're integrating. You could think of radicand when radicals, integrand integrals. Okay? And dx tells us we're integrating with respect to x. So if I were to say this aloud, I would say the integral from a to b of f of x dx. I could also say of f of x with respect to x. Both are fine. So today we're going to talk about how do we figure these things out. Let's get an example going here. Let's say we have the function f of x, which is x cubed plus 2x minus 3. And let's say we're on the interval 2 to 4. And our goal is simply to write out this integral, write out what the area under this curve would be, just to get familiar with the notation. So how would we do this? Well, we'll look back at this example and we'll say, oh, okay, here's how we do it. First, always start with the nice curvy s to represent integral. Here we were on AB. A was our lower bound, B was our upper bound. In this case, we're on 2, 4. So 2 is our lower bound, and 4 is our upper bound. Next comes our integrand, which is the function. In this case, that's x cubed plus 2x minus 3. Sometimes we'll put it in parentheses if there are many terms. That way it's clear that we're integrating this whole thing, rather than just x cubed, and then later adding on 2x and subtracting 3. And finally a dx at the end. And you might be thinking to yourself, oh, that's all well and good, but I don't really care about this. I care about what is the area, what is the value of that integral. And I'm going to say, whoa, hang on, don't get ahead of us, that's fine. For right now, we'll just worry about the notation. And I'll teach you a nifty trick to find the area itself. Now, this particular shape is a nice cubic function. You might imagine that the area is pretty large from 2 to 4, because 4 cubed you already have 64, so it's probably a pretty tall cubic function. But if I want to find this value, currently I don't know how to, but that is fine. What I will do is I'll use my calculator. So on my calculator, if I press the math button, math, and then I press number 9, which says fn int, or fint, your calculator screen should display a blank integral. Okay. All you need to do is plug in your bounds, your integrand, and an x right here to tell it what you're integrating with respect to, and your calculator will output for you a numerical value. So take a minute, try that, see how it goes. I'm going to try to hold up my calculator to the screen here to help you guys see that. So here's my calculator. Great. If I press math, maybe you can see that, maybe you can't. I'll scroll down to number 9. It displays this nice blank integral sign here. And I'll just plug in everything accordingly. So my lower bound is 2, my upper bound is 4, my integrand is x to the third plus 2x minus 3, and it's with respect to x. So hopefully your calculator screen looks something like this. It is possible that it doesn't. In the case that it doesn't, you should come chat with me and I'll tell you about how to input the correct inputs. But once you hit enter, it'll say, oh yeah, here you go. Turns out it's just 66. So in this particular case, our integral value is 66. Makes some sense, right? We expected it to be pretty large, even though it's on a small interval, because cubing something makes it pretty large pretty quickly. For now, we'll be satisfied with using the calculator to find integrals numerically. In a couple of days, we'll be able to have built up all of the necessary background to calculate that by hand, which is so cool, right? Being able to find areas of shapes that you should not be able to find the areas of, crazy interesting, and probably the best part of calculus, at least in my mind, is figuring out the formula for how to do that. So cool. You're gonna be so excited when you learn it, or you're gonna be really upset. But either way, you will not just be like, meh, whatever, I don't care. It's really provocative. So, what should we do now? Let's try one more, just to try on your own. So, let's do the integral from 0 to 2 of negative x plus 2 dx. I want you to just take a moment and try that out on your calculator, see how it goes, make sure that you can do it. I am going to do it out by hand because this shape is kind of nice. Right? You should never lose your intuitive feel for what this is asking. This is asking you for the area under the curve from 0 to 2. What curve? This curve. Great. So if I'm looking from 0 to 2, this is 2, this is 0. If I plugged in 2 for x, I'd get 0. If I plugged in 0 for x, I'd get 2. This is the shape that is made. This is the area of that shape. Well, it's just a triangle, right? The triangle has height 2 and base 2, so its area should be 2. This value is definitely 2. There will be times, there will absolutely be times when integrating it, even after we've learned techniques, is harder than drawing a picture and being like, oh look, it's a triangle, or being like, oh look, it's a circle. Please do not lose your feel intuitively for what this question is asking. By keeping that mindset, by reminding yourself, this integral is actually an area. Just like we remind ourselves, oh, this derivative is just a slope of a tangent line. We always want to keep the context so that we don't pretend, oh, math is just meaningless formulas and they give me numbers and they're not related to anything. Great. So, hopefully you got 2 on the calculator as well. If you didn't, we can chat. Maybe I did that one wrong and wasn't paying attention. Okay, so next question. Let's say this is my curve. Okay. The question is, I've always been dealing with situations like this first portion here, right? I've always had just the graph above the x-axis. What happens when the graph goes below the x-axis? Well, I'm not entirely sure. So here's what we'll do. Again, we'll call back to velocity. Right? We'll remember that if this happened to be a velocity graph, velocity versus time, when the velocity is positive, we are moving to the right. So we're going to the right, and that's great. When the velocity is negative, it means that we're traveling to the left. So if you were to calculate this area here, which we could do, right? This area is something, I'll call it A1, and this area is something else, I'll call it A2. And if I asked you to, tell me the displacement on this whole interval, we wouldn't add the areas together because that'd be kind of silly. Here you're moving to the right, here you're moving to the left. If you added them together, you'd be saying you're moving to the right in both cases. So what we do is, if we wanted to find the total displacement, which I'll call d, it would be a1 minus a2. Anytime you're below the x-axis and calculating an area, area we know is always positive, but below the x-axis, we're going to say that the area counts as a negative value. It takes away from some of the area above the x-axis. And we'll say this for the same reason we said it with the velocity graph here, is that you're traveling to the left, you're traveling in a different way. If it helps you to think about the height of this new area, you can say, oh, the height is actually negative. And we know that that's not true, right? Heights can't be negative, but we can think to ourselves, this makes some sense. And there are a couple of ways to think about it that make some sense. So if, for instance, if f of x is less than 0 on some interval, then the integral from a to b of f of x is no longer just the area under the curve, it's actually negative the area. Okay? Negative that area. It's a negative area. And that makes sense for this reason. hopefully you don't feel too torn up about that. Again, we could find the positive area and then just make it negative afterwards. The integral operation actually is really, really intelligent and already makes it negative for us. So that's really great. And then, of course, as we just mentioned, if you're above the x-axis sometimes and below other times, then your integral would take the first area and subtract, I shouldn't say the first area, the area above and subtract the area below. Okay, so let's do one last example here. What if I wanted to know the area under the sine curve from 0 to 2 pi? Well, I don't know what this is. So let me draw a picture for myself. Here's our sine curve, beautiful as always. And it's tough because this region isn't really a half circle, and I don't know what it is, and I don't know what this one is either, but I do know things about sine. I do know that the graph itself has really, really, really nice symmetry to it. And I know that it goes through 0 right at pi. And I also know that this region is exactly the same as this region, just that this one's reflected over the x-axis. So if I wanted to find this integral, I could say to myself, oh, I have this area above the x-axis and this same exact area below the x-axis, so this integral is going to be 0 for sure. For sure. Okay. So that's all I've got for you today. I'll leave you with one question to perhaps try out on your own. And you can try this one out by taking your best guess and then using FNint on your calculator. Should be fine. So let's find the integral from 0 to 3 of x squared plus 1. What I'd really like you to do is to try to take a guess at this using RAM techniques. So say, okay, last time we learned LRAM, RRAM, and MRAM. I'll pick 1, 2, or all 3 of those, test it out, figure out my best guess, and then try it on my calculator to see what we got. You might recall that we did this out, it was just x squared before, from 0 to 3, and we found that our best estimate was MRAM, and MRAM was 8.75, I think. So this one should be a little bit more with the plus 1, but try that out, see how it goes, and I'll see you in class.